Hello, we are discussing about response of low pass RC circuit for a pulse input. Look at the example pulse waveform shown. Here Vs is treated as input signal and this is pulse input. We can define in this way. Pulse input Vs is equal to V volts constant you are applying for the duration of t is equal to 0 to Tp. T is equal to 0 to Tp. Over this duration we are applying V volts as constant and Vs is equal to 0 for the rest of the duration for t greater than Tp. Okay. So input signal we are applying as two cases. One is a constant voltage V is applied for the duration of Tp seconds, and afterwards after that Tp seconds again the voltage applied is 0 volts. Okay. So response of the circuit is also of two cases. For the first case separately, second case separately. So first we will choose case 1. Okay, during 0 to Tp. During 0 to Tp, we are applying constant voltage V for a low pass RC circuit. Whenever a constant voltage is applied for a RC circuit, capacitor try to reach that voltage exponentially. That means capacitor starts rising towards that value exponentially. But whether it reaches that value or not, how much portion it reaches, that depending on the circuit time constant. Circuit time constant depends on the R and C elements of the circuit. So tau value is R and C, product of R and C. This is tau seconds. If, okay, first I am going with if tau is very small compared to pulse width. Tau is very small compared to Tp, and in general capacitor needs minimum 5 time constants of time to reach the final value. If you apply V volts, to charge towards V volts, capacitor requires minimum of 5 time constants of time. Here we are assuming tau is very small, so Tp is greater than 5 time constants. So definitely capacitor reaches that V volts. So initially we are not applying any voltage at t is equal to till t is equal to 0. So capacitor has not charged any voltage. So initial value of capacitor is 0 at t is equal to 0. From this onwards, as you are applying V volts for the duration of Tp and tau is very small, so it reaches final value. It reaches final value. At t is equal to Tp, it has got some maximum value. And afterwards, during second case, during t greater than Tp, greater than or equal to Tp, we are applying 0 volts. 0 volts is applying for infinite amount of time. Already capacitor has some storage, some voltage it has, so it discharges towards that 0 exponentially. And while it is discharging also, it based on circuit time constant only, that means tau, and our assumption is tau is again smaller than Tp, so it discharges towards 0 rapidly. It discharges towards 0 rapidly. So this is output response. Here V0, okay, and this is also V0. So V0 during this pulse width, V0 apart from the other period, that is after the pulse width, okay, and voltage arbitrarily whatever the value it reaches, that we assume it as Vp. So this is expected output response for the given pulse. We will see how to draw the equations later. We will go for the two more cases, when tau is equal to Tp and when tau greater than Tp. After going through those two cases expected waveforms, we will write the generalized equation. Okay. Say make it as V01 and V02. V01 is the output response during the time 0 to Tp, and V02 is the output response during t greater than Tp. Okay. So we'll go for the second case. Second case means where tau is equal to Tp. When tau is equal to Tp, that means the capacitor is allowed only for one time constant of time. Initially it has 0 volts, it is allowing only one time constant of time where it reaches 63.2%. That means 0.632 V it reaches. From that one, when you are applying 0 volts after t is equal to Tp, it starts discharging, and this amount is for infinite amount of time. So 0 volts is applied continuously. That's why capacitor discharges towards 0, but it takes longer time compared to the previous case. Next, third case. Third case is when tau is very large compared to Tp. When tau is very large compared to Tp, the voltage V volts is applied for shorter duration of time, but the capacitor requires longer time to reach that value. At that time, it reaches only a small portion of V. So you can draw like this. A small portion of V is reached, and after applying 0 volts, that is above t is equal to Tp, it discharges towards 0. Okay. For that one, it takes very long time. So this is output response for 3 different cases of pulse inputs. Now we will write the generalized equations. Generalized equations for V01 and V02. This is V01 and it is V02, where the voltage what it is reaching at t is equal to Tp is a constant voltage Vp. Okay, here also this point is treated as Vp, arbitrary voltage, and this waveform is related to the V01 and it is V02 of t. It is a waveform, that's why with respect it is time dependent, whereas at t is equal to Tp, waveform attains a constant value. That's why we are not writing of t. Vp is a constant voltage. Here V01 is function of time, V02 is function of time, but Vp is a constant at a particular time. Okay, we can define like this. V01 of t is the output waveform during 0 to Tp. V02 of t is the output waveform during t greater than or equal to Tp. Next we can write Vp is the voltage, is the capacitor voltage, that is output voltage, capacitor voltage at t is equal to Tp. Exactly at the end of the pulse, how much voltage charged by the capacitor is given as Vp. Now we will write the generalized equations for it. So we know the equation, generalized equation for a capacitor, that is voltage across capacitor at any instant of time is equal to Vc of t. Vc of t is V final minus V final minus V initial into e power minus of t minus ti by Rc. Okay. Now for t is between Tp and 0, during this portion, okay, what is Vf value, what is Ti value, what is Vi value? If you know these things, then you can easily write the generalized equation. So during this portion, V0 output response, that is capacitor voltage, is treated as V01. V01 of t is equal to Vf is V volts, Ti is 0. At t is equal to 0, we are applying V volts, and by that time voltage across capacitor is 0. So this will be V minus of V minus 0 into e power minus t by Rc. So it can be written as V into 1 minus e power minus t by Rc. This is equation 1. And at the end of Tp, that is at t is equal to Tp, we know V01 of t is equal to Tp is equal to Vp. Substitute this value in the equation 1. So we can write Vp as, okay, V into 1 minus e power, small t should be replaced with Tp. That Tp we will write divided by Rc. Tp is known value for the given pulse input, Rc is known value for the given Rc circuit, V is the applied voltage, that is also known. So after substituting the values, you will get a constant value which is treated as Vp. This is second equation. Third equation, that is for the duration t greater than or equal to Tp. T greater than or equal to Tp, again we are going with final value, initial time and initial voltage of capacitor. So at t is equal to Tp, what voltage we are applying is 0 volts we are applying, and the time, initial time at which 0 volts is applying is Tp. Voltage across capacitor at t is equal to Tp is Vp. Substitute these values in the general equation. So you can write it as Vc of t, that means V02 of t is equal to Vf means 0 minus 0 minus Vi is Vp into e power minus of t minus Tp divided by Rc. So it will be equal to, minus into minus it will become plus, Vp into e power minus t minus Tp by Rc. So this is third equation. You can calculate capacitor voltage at any instant of time by using these three equations. If you want to know the capacitor voltage, okay, if you want to know the capacitor voltage between 0 to Tp, V01 of t is the equation to be used. Okay, if you want to get the value at t is equal to Tp, Vp is the equation used, that is second equation. If you want to calculate at any instant of time voltage across capacitor above t is equal to Tp, you can use the third equation, that is V02 of t. Using these three equations, you can calculate the response of LPRC circuit for a given pulse input. So let us start one example. Draw the output response of LPRC circuit for a pulse input with 1 microsecond duration when fH is equal to 10 MHz, fH is 1 MHz, when fH is 0.1 MHz. First we will start with A. fH is equal to 10 MHz. fH is 10 MHz, and we know fH means upper cutoff frequency of low pass RC circuit. That value can be calculated by using 2 pi RC. So from this one you can calculate RC value. RC is equal to 1 by 2 pi into 10 megahertz. This mega, if it is coming towards numerator, it becomes micro. So this is 1 by 20 pi microseconds. Now RC value is known from the given upper cutoff frequency of a low pass RC circuit, and pulse width duration is constant. Tp is 1 microsecond. So we know this one, as well as we know Tp is equal to 1 microsecond. So compare these two values. First step is you must compare what is the value of relation between tau and Tp. Tau means RC. So this is tau. 1 by 20 pi is very small compared to 1. So tau is very small compared to Tp. That means capacitor reaches the final voltage. Whatever the applied voltage you will apply, capacitor will take that voltage at the end of Tp. Okay, so we can draw the response like this. If the input pulse is given in this way, if this is input pulse and this is Tp, okay, arbitrary voltage V we are assuming, and the output response is like this. Initially voltage across capacitor is 0. When the voltage V is applied for Tp duration, capacitor reaches the final value. Capacitor reaches the final value and it maintains that value here. and at t is equal to Tp, as 0 volts is applied, again because of small time constant it reaches that 0 value within no time. So we need to calculate what is the value of Vp. Vp is directly equal to V. Because capacitor is reaching the final value, Vp will be equal to V volts. Okay, now we will go for the second case. Second case where we are going for f is equal to 1 megahertz. F is equal to 1 megahertz. By that time tau is equal to, okay, tau can be calculated from this equation. Fh is equal to 1 by 2 pi rc. From this one, rc means tau, that you can write it as 1 by 2 pi into 1. So 1 by 2 pi microseconds it will become, and Tp value is constant, which is 1 microsecond. Again tau is small compared to Tp. Again tau is small compared to Tp, and it is greater by 2 pi times. 2 pi means 3.14, pi means 3.14, 2 pi means 6.18. Again the same thing, it takes some amount of time and reaches the final value, and again it discharges towards the final value by taking some time. That time is always equal to minimum of 5 time constants of time. Okay, so capacitor reaches this value. Again it is Vp is equal to 5 volts. Sorry, Vp is equal to V volts. Next, third case. Where Fh is given as, third case, Fh is given as 0.1 megahertz, whose equation is 2 pi rc. From this one, rc can be calculated as 1 by, okay, 0.1 rc, 0.1 into 2 pi, that is 0.2 pi microseconds. So this will be equal to 0.2 into 3.14, so it will become 0.614 microseconds. So this RC is now greater than TP, because this value is greater than 1 and TP is equal to 1 microsecond is given. So definitely capacitor cannot reach the final value, capacitor reaches some arbitrary amount. From this one, capacitor discharges towards 0 after taking longer time. Okay, now we need to calculate what is the value of Vp. Vp can be calculated only if you know this voltage waveform. That means V01 of t. So first step is you must calculate V01 of t. V01 of t means Vf minus V final. Already we have seen V into 1 minus e power minus Tp by Rc, e power minus t by Rc, t by Rc. After going through this one, at t is equal to Tp, V01 at t is equal to Tp is termed as Vp. So V into 1 minus e power minus Tp by Rc. So you can write V into 1 minus e power, Tp is 1 microsecond, whereas Rc is 0.2 pi. So substitute these values, you will get the value. That value you must indicate on the waveform as Vp. No need to indicate the waveform equation for V01, V02. Okay, you must able to write the equation. Vp you should indicate. So from this question you can draw first expected waveform by comparing the pulse width with the circuit time constant. Once after comparing, you can easily get the relation. From that relation, whether the capacitor reaching the final value or not, that we can ensure. Accordingly you have to draw the expected waveform. Okay. Now second question. Draw the output response of low pass RC circuit when Tp is 10 RC, Tp is RC, Tp is 0.1 RC. Again the same thing. Okay. Tp is equal to 10 times of RC. That means Tp is very large compared to tau. That is, tau is very small. And Tp is equal to tau. Tp is very small compared to tau. Okay. Same as previous. You can draw the arbitrary waveform and get the equation. This you can do it. Next, prove that by direct integration the area under input pulse is same as the area under output waveform of low pass RC circuit. That means area under capacitor voltage waveform. We are going to prove area under the input pulse is same as area under the capacitor voltage waveform, which is nothing but response of low pass RC circuit. Okay. How to prove this one? This is input pulse. First we will draw the input waveform. This is input waveform and area of this input waveform is this one. Area of input pulse. So one edge of this square is V, the other edge of this square is Tp. So simply V into Tp is the area of input pulse. You must get the same area when you are going to get the area under the output waveform also. So this is arbitrary waveform which I am drawing. So this is area of output waveform during 0 to Tp and during T to Tp, T greater than Tp. So output waveform has two different areas. One is within 0 to Tp and the other is T greater than Tp. So make it as this is V02 and it is V01 of T, V02 of T. So area, total area of output waveform is equal to area under V01 of T plus area under V02 of T. So area under V01 of T, where V01 of T is equation is V into 1 minus e power minus T by RC and V02 of T is equal to Vp into e power minus of T minus Tp by RC. These are the equations to be substituted. Already we have seen, we have derived these equations for a pulse input. So first, area under V01 of T. Area under V01. A1, let A1 is the area under V01 of T. So area can be calculated by integrating the V01 curve. So V01 curve has the limits from 0 to Tp. 0 to Tp is a V01 waveform and Tp to infinity is V02 waveform. So integration with limits as 0 to Tp, V01 of T into dt. V01 of T already we know it is V into 1 minus e power minus T by RC. Take integration with limits as 0 to Tp. V is a constant kept outside, one integration is T and e power x integration is again e power x, okay, and divided by the text differentiation. So this is 1 by RC, minus 1 by RC and this minus get cancels, it will become plus, minus into minus, and next RC into e power minus T by RC with limits as 0 to Tp. Now substitute the limits and simplify. After substituting the limits and simplifying, you will get A1 as V into Tp minus RC into V1. This is first equation. Area under V02 of T. Say it as A2. A2 is equal to, it is limits from Tp to infinity, V02 of T. V02 is already defined, Vp into e power minus of T minus Tp by RC into dt. And Vp is a constant, e power x differentiation integration is e power x with divided by differentiation of that value x. So after simplification, it will be looks like minus Vp into Rc. This is minus Vp into Rc is second equation. Total area under output pulse is A1 plus A2. So Vtp minus Vp into Rc plus Vp into Rc is equal to Vt. Vtp this is. So this is exactly equal to area under input pulse. Only one important thing you must remember is while going for this, V into 1 minus e power minus Tp by Rc, this whole term can be replaced with Vtp. Replacing with Vtp, that's all.